Please signify if you can hear the speaker, please. Can you hear me?
Yes, we can.
All right, thank you very much. Thank you for the introduction. It's a pleasure to be here on this Saturday afternoon. Uh, like I was introduced, my name is Peter Oladipupo, and today we'll be talking about process simulation, modern process simulation, LensaSim. And I would like to start by uh, okay, I would like to start by introducing myself in greater details because this would provide context and substantiate the essence of today's topic and why process simulation is very important. Okay, I want to convince you on the essence of process simulation. So let me introduce myself to that. So, like I was introduced in the introduction, right? I did my PhD in chemical engineering at Purdue University, and and my first major exposure to process simulation was during my PhD, right? Exposed to some extent while I was an undergraduate at University of Lagos, particularly in my final year, where we some guys came to campus there to introduce process simulation to us, right? They told us, oh, this is required to enhance your employability, right, in the job market. So we paid money for some training, and then I learned some process simulation. Okay, so my thought then was, okay, this is an industry skill, right? An industry tool that is important in industry. So I did not really connect how relevant and important it is beside helping me to get a job. Do you understand what I mean? Right. So it is not until when I was doing my PhD that I find out really how important process simulation is. Okay, because I can tell you for a fact that process simulation was majorly the tool I used for my PhD program. Right. There are different kind of PhD programs. There are experimental programs where you usually spend most of your time in a laboratory, right? Setting up equipment, setting up physical equipment, and then testing hypothesis, right? You'll be surprised how much you could also do with process simulation, just sitting down on system, and then simulating processes and then coming up. And because of from that, the work I did with some of my colleagues led to granted US patents. If you understand how the US patent works, it has to be novel, non-obvious, and useful. Okay, so you could, it is not any experimental work that led to this patent. It is work based on process simulation. You sit down with this simulation software. You spend a lot of time, you generate hypotheses, you can do a lot. So I want to show you all of this today, right? So that's why it's important for me to introduce myself in details. And it is those from those inspiration as well that led me to finding my own company for developing chemical plants, right? To produce basic chemicals that are otherwise imported into Africa. So if you ask me what has been the most important skill, that shaped my career, it is process simulation. You understand, right? And that's what led us say, okay, we started lesson technology, and process simulation is about the very first product that is live, because we find out how important this is, and we believe it is not fair the way, especially in Nigeria. In the US, as I will explain later, you see how important it is in the academy already. So, but I think we are not placing much emphasis on it here in Nigeria. Okay. All right. So now, what is process simulation, right? This is one of my favorite definition I came across online. As you can see, very simple. A computer-based mathematical model used to represent and analyze industrial, chemical, or physical processes. Keywords there are represent and analyze, right? I want to go to those two keywords: represent and analyze. So it's a computer-based mathematical model. It's a mathematical model at the end of the day, a chemical plant, right? A chemical plant that is a physical facility, however big it is, even if a chemical plant is as big as covers the entire of Lagos State, at the end of the day, there are systems of equations, that happen to be made of steel. That's what they are. So you see all those unit equipment, all those physical facilities that you see, you can, and even the geometries. Of the facilities. So that is what makes process. Imagine having them representing software, and then you can play around those equations and to generate things. That's what it is. So you use process simulation to represent. You understand what I'm saying? So that is, I want to hold on to that. Air Force commercial program of process simulation aspect the importance of this, right? So they funded a program to develop this kind of solution because they know how it's important. It's going to be important for education and research and even industrial innovation. So that is what process simulation is. Right. Now, in my experience, there are two core use cases of process simulation, two major use cases. That is process design and process synthesis. Okay, process design and process synthesis. Now, process design is just like what you said there. If you are given a flow sheet, the task is, can you size and optimize this flow sheet? What does that mean? For example, a common petrochemical process is steam cracking of ethane to ethylene, right? This is a standard process that has been developed for decades. I mean, it's been developed and commercialized for decades. So you can say, relatively, there's nothing much new about it, right? So let's say, let's say we discover some natural gas we want to commercialize in Ikeja, okay? And we want to just want to convert it to ethylene and sell, because we know ethylene is a major petrochemical. I mean, huge market, over $200 billion in market size globally. So there's market for it. So it's a no-brainer. So we want to set up a steam ethane cracking plant, right, to produce ethylene. Of course, we know it's a known process, right? It's known that it's nothing much to be done, but you still need to put it on paper. I mean, you can't just put your money and just invest $1 billion to build a facility, and you don't have no business. I mean, you are going to risk the money, and you also go to risk lives, right? So what you use process simulation here to do is to just validate that known design. Does that make sense? We know a design already. We know that. So you set up, given your own constraints and parameters. Okay, is a gas found in Ikeja here, right? This is the source of the chemical, of the feedstock. It has its own unique properties, right? So we just play around the data, right? Around that feedstock, its properties, and then adjust it accordingly using the same standard way of doing steam ethane cracking. We know how it's done. There could be spill changes. So we use process simulation to validate that design, okay, on computer. So, and when everybody is satisfied, then you optimize, you come back and say, oh, can we minimize the cost? Can we even save further money, right? We can even do better than it was done maybe in the US, so, but it's still around process design, right? Then you do advanced detail engineering, right? They do TNI, they validate it, and then you move on to construction, right? So that is one common use case for process simulation. Now, a more interesting use case, I will tell you, a more interesting is process synthesis. This is where most people don't know how powerful. This is a realm of limitless possibilities as far as process simulation is concerned. Now, process synthesis means given objectives and constraints, you don't have a process, right? Find the best process flow sheet. Okay, let's go back to that same problem of we found a natural gas source here, and we are thinking, let's say we want to produce ethylene, in fact, at the same time. But because let me give you something I've realized is that one of the major reasons why we don't have much industrial development, at least right now in Africa, is because of, these things cost a lot, right? They're very expensive. Chemical plants, you need billions of dollars, especially if you are maybe like a Dangote, right? Or some other giant companies that can invest. So it's difficult to find the resources, you understand, to actually invest in building a chemical plant. They are not cheap at all. So, but let's say, because we know they're not cheap, right? But even at that, we want to find a way to do this at a very lower cost compared to the standard way doing it. Maybe standard way will cost $1 billion. I want to do it for $100 million. I mean, it's a very bold vision, right? So, and that would mean forgetting the norms. Okay. If we are going to use the standard way of doing it, it will cost the same thing, about the same thing. And someone said, okay, let's try alternative processes. Okay. And then with process simulation, you can begin to play around flow sheets. Of course, because the way process simulation are designed, they are based on theories. I mean, the theories we learn in classes, right? The thermodynamics, the reaction engineering, the separation engineering. These are the guiding principles, right? So you then, based on what is permissible, right, in doing that in that environment, you then begin to play around with flow sheets and begin to come up with alternatives. I tell you, you will be so surprised with what you discover. In fact, there's a lot of opportunities here in chemical engineering because it is usually forgotten that, oh, we know how to do it, just like I explained to you. If today they want to design, they want to convert, add value or valorize a natural gas feedstock, the natural thinking will be, okay, let's build a steam methane cracker plant, or maybe some other plant that are known standard, right? Not many people, because you only have few people with that much investment that want to invest, and they want to play safe. Do you get my point? So, but there's a lot of opportunity here. This is what then, the way it works in the US is when you discover this kind of, when you do a lot of play around with flow sheets like this and generate option, then you now do what is called bench scale study in the lab, right? You do bench scale study, a more advanced study, then you do pilot plants. You know, all those then validate. Before you know it, you develop a new process. And you develop something that is patentable. Develop something, maybe there's a new technology just came out from there. And before you know it, your name is attached to a technology, and maybe you even make more money than or save more money compared to what other plants are doing. So the process synthesis is a major use case for process simulation that I think we need to lay a lot of emphasis on, because it's a world of limitless possibilities. Like I said, you can virtually develop anything. You understand? Of course, there are principles, and the system will always tell you that no, this will not work. But as a chemical engineer, with your intuition, right, is a way to actually test your core skills, right, and actually even develop yourself, you know, and learn a lot. So with that, of course, and the really what impacts, I mean, as I would think that they are obvious from what I just explained, right? For students, hands-on experience, you know, see, for a student, the best you get close to it, besides visiting a physical plant, the best you actually get close to a physical plant is actually process simulation, right? Because you can interact with a virtual form of what is available physically. You can interact with it on your computer and say, okay, this is how this works. Or maybe they taught you something of reaction or equilibrium reaction, right? If you want to see, okay, what does that really mean? You can come to a process simulation software, open it up, and play with an equilibrium reactor, and then begin to see what's going on there. You understand what I'm saying? So that way you begin to appreciate, you know, the theories that have been taught in class. You get what I'm saying? Me, I would say that if, for example, when we were in college, right, when we were being taught all these concepts, chemical engineering concepts, if we have this tool as part of our curriculum, I'm not talking about, okay, something you learn, like I said, because you want to enhance your employability skills, right? I'm talking about something that is part of my curriculum from under level. You know, I believe I would have gone further than I've gone today, because I will appreciate the concept better. You understand? And then I can then use those concepts to even do more things. So hands-on experience, you get stronger skills, right? And better outcomes, right? Improve understanding, improve confidence. You understand the concepts at a deeper level than you ever have come across. Because this simulation software, like I said, it has all these theoretical principles beyond even what you have in your textbooks at PhD, beyond at PhD level, because those are the concepts that actually guide development of these things. You understand? So, of course, enhanced teaching. Imagine, like I said, imagine the lecturers bringing this concept to the classroom, using it to aid teaching and learning, right? The students better learning outcomes. And of course, the industry applications are, I mean, a no-brainer. I mean, you can never emphasize it, right? It's important. Even for someone that maybe your job is not does not really relate to using power simulation every day, you can use it to even get ahead, because you can simulate and get better understanding of the process you're putting. Maybe you're a plant engineer, right? With simulation, you can get a better understanding in your process, and maybe be able to suggest recommendations that even add more profit to the company. And I mean, maybe get the person information. You understand what I'm saying? So the impact and there's some evidence, to corroborate this impact, right? Project causes of some studies, right? In the Journal of Natural Gas and Engineering, and 46 independent academic studies have confirmed the massive gains, the massive gains in engineering learning outcomes from virtual labs and simulation, something like this. Because employers, 92% of employers, would naturally are interested in students or candidates with expertise or skills in process simulation. So it's just the benefit that just massive. All right. So with that, this is going to be a short presentation. What I really want to do is to demonstrate for you how this works with our software solution called LensaSim. Okay. So, and I'll tell you why we built LensaSim. Now, like I told you, even when we were undergraduate and trying to assess, it was difficult to assess this software. Commercial software like Aspen, they cost about $70,000 per user per annum to assess the industrial software. That's about 100 million naira. Imagine how many people can afford that, in a place like Nigeria. So they're actually very expensive software. It's expensive solution. Very, very expensive. I mean, if you assess it, so there are academic licenses, right, that is subsidized for students, okay, for schools actually, but it's still, you're looking at $30,000, right? The school pay about $30,000. That is, you're looking at up to $50 million, right? And then they would give access to a number of students. You get, these are still very expensive. So if you have access to it by any means, I can guarantee you they are illegal version. You understand what I'm saying? So, but the real software themselves are very, very expensive. So that's the motivation behind us building LensaSim. Because we understand the importance of this software, of this solution. So we want to put it in the hands of everybody, okay, especially students, employees, and lecturers, right, to be able to lay their hands on power simulation, appreciate its importance, and make it a key part of learning, key part of teaching, and key part of doing your everyday job. You understand? So that is why we put LensaSim, because we want to democratize access to simulation, because we know it is very, very important, and it is a tool that we are taking for granted. For example, in the US, in the school where I did my PhD, so I was a teaching assistant for 2 semesters, and to the two courses, the courses I was assistant for were process design. They are penultimate courses. Now, that course, if you can't pass it, of course, if you don't pass it, you're not graduating, of course. Now, that course is all about power simulation. So what they do is they have teaching a lab, or a computer lab. Students come in, right, every week. The 16 weeks of program, right? You go through, you learn one thing or the other, right? And then that's for the first part, Then there is a design course, okay? You have to design solve a problem. After learning the basics of the simulation software, then you now in groups work on a project and use this simulation software to actually solve a problem. Yes, and then that becomes what they present. And I tell you, some of them will come up with novel stuffs, that became part of their resume. So it's very, very important, and it's, like I said, it's a core requirement. Without it, it's not. So there in life, for example, some people use simulation for their education, right, for their project, but it is not a requirement. You see the difference, right? It's not a requirement. You just do whatever you want, but it is a core requirement because they understand the importance. Okay, all right. So that is why we LensaSim, to ensure that everybody has access to it. So what I want us to do now is to now do a live demonstration, right? How does LensaSim work? So if you have a laptop, you can follow me as we do some one exercise. Just go to lensasim.com. So I'll stop sharing this, and then I'll go to the platform live and do some exercise. Okay, so this is LensaSim.com. So I want you to follow me as we just do a simple exercise. And what I want to do really is to actually show us in details how the different layers of the platform works. Okay, and see how interesting this is. Okay, so I mean, you can just go right ahead and start simulating for free. I mean, or just open the simulator. You can open it, right? So, exercises. Okay, you can just open simulator and you're off to the races. Okay. But it is advisable you sign in. And you're not, I mean, signing in does not cost you anything. And in fact, we are not, doesn't require you your data or anything. You put your email address, it sends you a code, you just input the code, that's all. Your data is not in. So I'm going to type my email. So I expect to get a code, which I'll then impute. Okay. Okay. So I mean, I would advise to do the same, right? To sign in because that way you get as more access to certain things, right? All right. So you're going to open simulator now. Okay. So you're going to open simulator, right? So as a first-time user, the first thing you will see is you see that there is a guide. The platform has a guide, right? To essentially to guide first-time users who are anybody that has not used simulation software before. Okay, and another thing I would say about this, how beautiful this is not you don't need to install anything. Okay, it's web-based. It's entirely web-based, right? You don't need to. I mean, conventional simulation platforms, you have to download the software and then install. This all you need is internet. No heavy, nothing heavy. Okay. So you can. So we start from blank, of course. Like I said, you can. There's a guide. So what the guide does is just guide you through the process. I mean, you can use it. You can do that if that's the first time. Just to get yourself used to it. But for today, just turn it off. Okay. All right. Now you will see that to the left there are 6 environments. Okay. You have performance environment, simulation environment, analysis environment, energy environment, economics, and safety. All right. All these are important, and we'll go through all of them. Okay. But and please feel free to ask me questions, stop me and ask questions as we go along. For any simulation, right? For any simulation at all, in any case, where you want to start is the properties environment. All right. So it is in the properties environment that is where you specify the parameters and the components that are participating in the processes you want to develop. Okay, that is if feedstock, right? That will be participating in that process. The products, intermediate product, any other thing that any species or any material that will be involved in one way or the other in the processes, right? You need to specify them in. Besides that, you also be specifying thermodynamic parts. We'll get there. So first, let's start with the components. Right? The component are the species. Okay. So for today's exercise, I want us to work with steam cracking. I mentioned it earlier. Right? Steam cracking of a thing. It's just a simple part of the one. We are not going to. It's a complex process, so we are not doing the complex thing. So we're just going to take the cracking part of it, essentially. Okay. Reaction, cracking, reaction. Right, and that's important essential thing. So we have a search button here, right? So anything you can't readily find, you can always look for, right? So let's look for a thing, right? That is a primary component, okay? That is involved. That is primary feedstock or raw material. Of course, when you crack a thing, you produce ethylene, right? Produce ethylene, and then of course hydrogen as a byproduct. Okay. Then other thing that is involved in that reaction is steam. That's why it's called steam methane cracking. All right. So steam is involved. So steam is an input. So we specify steam. So that is water, right? From steam to water. Okay. All right, so these are the components, current components we are dealing with. All right, so you specify the components, so 4 components, right? So the next thing you will see after one, the next is property method. Now, property methods are thermodynamic, let's call them predictive systems, essentially. What they do is, given your component, given all the species that will be involved in these processes, what are the best theoretical underpinnings, right, that can best predict their behavior? Do you understand? That will best predict how they will react, how they will behave. That will most accurately predict how they will behave under the condition you want to subject them to. That's what we call property package, right? So there have been researches and works that have been done over the years to develop these packages, right? And there are different of them. So we have a picture in everything to suggest for you what you should do. But of course, you can always do research yourself and try to understand the basis behind all these things, right? Like there's ideal law, right? About law, there's Robinson, which is being suggested to use now. Let me show you that one available there. There's SRK, PSRK, and NRT. So these are packages. It involves series of equations, right? Thermodynamic equations and models that I believe will best predict the behavior of these components. Does that make sense? Under the condition we are going to be suggesting them to. So let's go with Robinson. Okay. So you choose Robinson and then click on continue to simulation. All right, we can also come and click on simulation here to the left. All right. So click on, yes, please.
Yeah, click this continue simulation or this one.
Anyone, they are both the same. Do you understand? So we can, let me show you. Go to click on simulation, see what we have, see what we specified already here, right? Consider, right? So let's go back to. So it's the same thing, it doesn't matter. This is just a guide. I mean, for someone that is just getting to use it, right? You say, okay, continue to simulation, right? So let's do that. All right. So this is the simulation environment, right? So as you can see to your right, what we specified are reflecting here, right? We specified ethane, hydrogen, and water. And you can always go back and edit them. You can add components, or remove anything. Right? To the left, these are representative models of the physical units that are typical for a chemical plant, right? From reactors, separators, right? Heat exchangers, and the likes. So you have them here, right? Show you that. So you see, see different units as we show you, right? So you can always go down and say. Okay, so now let me tell you something. There are about 34 units here, right? Models here. But in reality, you have hundreds of different units. So the one core skill of a process simulator is to understand, because in reality, you can't really represent all of them as they are, really. Is not, that's why there's what we call detailed engineering. You do more engineering studies, right, as we go along. But it's skilled process simulator will know what model can best approximate the what is obtainable physically. Do you understand that? And it's based on your understanding of the process of the reaction of the process that is taking place. And then you can, what a simulator does for you at the very least is helps you calculate material and energy balance accurately. Okay. It calculates material and energy balance. Other things you can't guarantee, right? For material and energy balance is primarily what it does for you, and that is what you need to to do your basic design and process synthesis. You know what I'm saying, right? So you come here. The first thing we do is to subscribe feedstock, right? Coming in goes to a unit. So the feed. So click on the feed, and you can see here it's pairing, right? Let me it down. Okay, so the feed, right? That is the ethane that is coming in. But it's ethane and steam. So, but let's supply ethane now. So by just clicking on it, you see what is over to the left. Form, a specification form. Because that feed is coming in at certain conditions. It's coming at a certain pressure, it's coming at a certain temperature. And of course, a certain flow rate, that is amount of it. So we use standard, 30 degrees Celsius. Let's use 2 bar. Okay, pressure of 2 bar. All right. Now the flow basis, it can be mass flow rate or there are different options. We're going to choose mass based flow basis. Okay. then total flow. Because once you change this it reflects here. If you have to choose more flow rate, for example, you have more flow base. But there's no mass flow. This is just an assumption, anyway. All right. For this is an assumption as well. So we're going to let's assume 1,000 kilogram per hour. All right. That's just flow rate. Just an assumption of how much of the thing they are. Then so this is mole fraction. And that in reality, the ethane feedstock that is coming in is not pure, right? It has ethane, it has propane, butane, other higher hydrocarbons, and even some other impurities. For this exercise, we just assume it's a pure ethane, okay? All right, so just to demonstrate how this works. All right, so we're going to assume it is 1, and this pure means the mole fraction is 1. It's the only thing there, okay? So with that, we specify the feed. So this feed is specified as it is. I can rename it. Let us rename it as by clicking it, we name it as a thing, right? Okay. So that is our ethane feedstock. So again, steam ethane cracking. You mix, how it works is that steam is mixed with ethane. Okay, for steam ethane cracking unit. And then it's sent to a furnace, a cracking furnace inside. So the steam, so we're going to find another feed, all right? Another feed stream for steam. So this is steam. I hope you are following me for those with their system. They will specify the steam condition as well. For the steam, because it's steam, right? Typical condition, entry condition will be heated up, usually 620 degrees Celsius. Typically from 500 to 680. That is the steam should be heated to that, should be heated to that amount, right? So just 620 and pressure of 2 bar. Now the basis, there's a more feed ratio. For every 1 kilogram of ethane, you want to feed in 0.35 kilogram of steam. Now, all these data that I'm reading out to you are standard way of doing it. So this is a classic process design. We're not doing synthesis here. So do you understand what I'm saying? This is a classic process design because I'm just using data that are available. If you want to do it personally, we just ignore that and start playing around, data and seeing what we can get. You get what I'm saying? Okay. So 620 and 2 bar, right? And then the flow rate, because it is 4.35, eh? 350. Is that what you said? Yes, correct. 350, right? But 0.35, just 0.35 times 1,000. So 350 kilogram. Okay, and the mole fraction is what? What will be the mole fraction? Right? 1. So that is fully specified. All right. Now notice that it's entering at 30 degrees Celsius. I mean, just as a feed at ambient condition, right? 30 degrees Celsius, and the steam is at 620. So ideally, the steam will also need to be preheated to be at the same temperature as steam before they are mixed together, right? Conceptually, they need to be at the same temperature so they mix together. If you mix them together at this, what will happen? Temperature will drop, right? The mixture will drop. You don't want that. So the temperature of the operating condition for steam cracking is around 850 degrees Celsius to 900. Okay, so let me explain the theory behind it. So the steam cracking reaction are very high temperature endothermic reaction, and the reaction takes place in residence time. Can anybody guess, or does anybody know the residence time for steam cracking reaction? Nobody know. It's under 0.2 seconds, right? It means the reaction must take place in 0.2 seconds, less than 1/5 of a second. So you know why? Because if it's longer than than that, there will be side reactions. You start other things start happening. Okay, so the reaction has to be very quick. So the feed is coming in at 620, close to the not hot enough, and you will see some from the analysis we'll be doing. Not hot enough to start the reaction, but also close enough so that by the time it is entering the reactor, there is a quick reaction takes place. It quickly rises to 850. Reaction is done. Quickly cool it down. The quenching. It's an interesting process. Cool it down with the quencher, right? And then to preserve the NP at 620, you understand? Okay, a preheater, all right, or heat exchanger for the ethane. So we come about and pick the topic. So we have this heating unit here, heat transfer unit. So we pick an heater, right? Okay. So this is an heater, just come to the and just drag it and it's connect like that. Okay. And then you can drag this as well here. For the product, this is the outlet once it is heated. So by just all you have to do is just click on this heater and then it should spy it. So it's simple. All you have to do is just spy the outlet condition, outlet temperature of 620. Right? Now that's it. Currently there is pressure drop, there will be some pressure drop. But just for now, let's just assume there's no pressure drop. Okay. To simplify what we are doing today. Right? So at 620 degrees Celsius, let's see if there's anything else. That's all right. So let's specify. So we can run it. Okay, it's now this is complete setup. We can run. Okay, not yet because we need to. This is empty, right? So we have the ethane, the ether, and the product from the heating, right? Now, then we need to mix these two together. Okay, so we use a mixer. So we have a mixer. Turning the two this to this phase. Right? And then this here. Okay. So the mixer, we are not to specify yet, right? Just 3 inlets. Except if we have more inlets. Okay. So we can run this. Let's run this and see what we have. Okay. Oh, this is not connected, so there's an error, right? This needs to be connected. You don't have the product, so as you can see the error, right? So it will always tell you that if you're not, if not something correct. So let's run it again. Okay, now combine. So what we have done, is just to heat up the ethane to 620 and then mix together. That's all. And mix it with steam. And let's just quickly see the result that we have, right? Okay, so you can see, right? This is just to which one is S1? S1 is the ethane, right? And S4 is the product, the mixture now, right? So S4, you can see, right? What does it contain? Let's look at the mass flow rate, right? It has ethane, right? Of 1,000, right? And then water, and then steam. Right. And then the temperature is 620, just like 160. Okay. So what we're doing we've only done two things essentially. We heat ethane to 620 and then mix it together with given steam. Okay. Pressing. All right. So now let's move it. Now move around the palettes to the screen. So now the next is going to the reactor. Okay. This is where like I said, so the typical, if you do a Google search, you can do it and look at steam ethane cracker. To see how it looks like. Just take a look how it looks like. It's a giant industrial furnace. Okay. Yes. It's not converging. Let's read here. What is it telling you? Feed requires prescription before solving. So this is not specified, right? Click on it. Can you see? Temperature is not specified. 620. That's what we just did. Right? Yes.
That's fine. It's not connecting.
It's not connecting. You're not able to connect it. Let me see. See this. When you just put your journal, you see the sun come on. That's what you're doing. Like,
How you read that? You understand what you meant.
yeah, it's wrong. Yeah. So that's what you drag. So you have to be careful with the dragging. Okay, any other question before we move on? Any other question?
Yeah,
Okay. So I was talking about how complex a typical industrial furnace ethane cracker is. It's a giant furnace, right? The giant furnace, and what happens is you have the furnace at the bottom of the furnace, like it's a giant structure, right? At the bottom you have methane, natural gas with air combusted, right? So the heating takes place, rapid heating is taking place. So heating up to supply it, just like cooking, right? So you cook it up, I mean, you combust it at the bottom of the furnace at a temperature of 1,500 degrees Celsius, almost 2,000 actually. So as then the feed, the feed that you want to crack, it's coming in through some pipe. There's some pipe transfer line exchangers, right? Some kind of plug flow reactors, right? That comes in lined up, they're just lined through the furnace from the top. So they're coming in at 620 degrees Celsius, preheated at 620, and then they're flowing down. Okay, so the reaction takes place somewhere towards the lower part of the furnace, right? As the hot gas is coming from the bottom, it's contacting the pipes. You understand? And heating them up so that it takes them to 850, and then the reaction takes place, and then quickly goes out, goes back up, and then exits. Does that make sense? So and then exits, and then quickly gets cooled. It's in fact the steam is heated up in that way as well. So that giant infrastructure does the job of producing your steam and doing the preheating as well, because the heat is recovered. I mean, you are generating it up to almost 2,000 degrees Celsius. So it's recovered throughout in doing preheating work, in doing heating up the steam, and doing all of that. You get it? So that's what it is. But the core of the reaction taking place is an equilibrium process. I have a slide for, I don't think if I can go back there. So what's happening is, so C2H6, that's ethane, right? It's like you crack it. That's what's happening. Crack it open. They are very strong bond. Methane is the most difficult hydrocarbon to break, right? You know that, right? The second is ethane. So that's why you have to supply they have to take place at high temperature, right? So it's very difficult to break. So you need that high temperature and there's of steam to do it. And when it breaks, what's happening is that hydrogen is knocked off. C2H6, you remove hydrogen and you're left with C2H4. So it's an equilibrium process. So as the temperature cools down, it goes back. Okay, ethane can react back with hydrogen, goes back to ethane. Do you understand? So it's an equilibrium reaction. It goes back and forth, right? So because it's an equilibrium reaction, you can always model that kind of process with an equilibrium unit in a simulator. But that's it. So if we want to, what we are doing today, we've done heating, we've done mixing, and we are going to specify a reactor now, and then we complete the process. But if we want to do the entire modeling, we can do the entire modeling of a cracker. Yeah. Right? But in the industry, it's one giant unit, majorly. But you want to model it, we can do it. Maybe I'll be using like 15 units. But you'll have modeled the entire thing conceptually. Because you'll have modeled the preheating, you have done you have done the recovery of the heat. Because after this reaction, you do it now, it will be coming out at the high temperature. You use heat exchanger, right, to cool it down. We do all of that. And you would model a system that is representative of what you have in, right? You understand what I'm saying? So I want to understand how simulation works. It's not as if you see that there's that thing you have is what you model. No, you have to be able to model it conceptually and be representative, right? That would be a difference between you modeling doing a simulation. So if I were a lecturer grading maybe you do the simulation, you do the other one, and give you the same script, I'm sure you come up with a different thing, different design. You understand what I'm saying? So that is the way of testing your skill, your understanding of the process. And what? So here we have an equilibrium reactor. Go to the reactor, right? So you see different kinds of reactors. Model, yes, right? We have conversion lead reactor, equilibrium Gibbs. So let's use the Gibbs. So Gibbs reactor is one of the best for this kind of thing, and I'll tell you why. Gibbs reactor just it does the job for us seamlessly because Gibbs is based on minimization of the Gibbs free energy. So it calculates the reaction the way it should occur to attain equilibrium. Simple, that's what it does, right? That's what Gibbs reactor does. You can use it as a equilibrium model using substitution, but Gibbs reactor, you don't need to do anything. Just do the calculate the minimum free energy, and then based on that, to get your product, right? So Gibbs reactor, then you just send this in, right? For those someone was finding it difficult to do this, so once you bring your mouse, you see the two dots appear, two separate, something like that there. So it's one of them. You click with one, right? Just at the very end, and then you just move it through and it connects. Okay. So the products, what is the product stream? Now these are energy stream. You don't need it. If, for example, you just want to represent the energy that is coming out, okay? You want to show, you can drag it out. It's just represent because this is an energetic system. You are supplying it of heat. Okay, you understand? So this reactor, just to specify it, anything to specify there is the outlet temperature. That's all we need for use. It's that simple. So the temperature that is operating temperature at which the system is 850, like I told you, right? Again, in reality, is a profile, it's a temperature profile in reality, right? It's 620, it rises exponentially to 850, and then that's actually the real profile. But here we are approximating it as what approximately, let's say 80% of the profile is at 850. You understand the concept, right? So 850 degrees Celsius. And typically there's pressure drop, right? Or let's instead of using pressure, the pressure drop, this was 0.1 typically. Okay. We can specify it in another way because I want to do analysis. I want to show something. So I will use operating pressure. All that means that it will no longer be 2 bar, it will be 1.9. Does that make sense? Since there's a 0.1 bar drop. Okay. So that is specify temperature and operating pressure. Then we can run it now, right? Let's see what combine, right? So let's look at it. So let's see what has happened. Okay, so the product is S5, right? So this is actually let's first rename this one. So actually the string that will appear S5, right? S5. Let's look at S5. So this S5, the products. So let's look at what has happened to ethane. Look at what has happened to ethane. From 1000, it has gone down to 210. It means 719 kilogram per hour has been converted. So the product that is coming out contains, as you can see here, ethylene of 737.1 kilogram per hour. That's the product. Hydrogen of 2.97 kilogram per hour, right? And then ethane of what? 210. So this ethane has been converted to this. Do you understand? Right? This ethane of 1000 has been converted to 790 of it, right? Has been converted to 737.1 and to 2.97. Which balance? The mass balance, right? Because you are left with 210 of it, 790 has gone and converted to 737 for ethylene and 2.97 for hydrogen. Does that make sense? Now, this is a parameter that's important in the industry. Conversion of 79%. That's very good, actually. So typically you optimize for conversion of 80%, then you recycle the rest. Then you design recycle the remaining, you separate it, do some separation steps, and then recycle the ethane later, right? Yeah. So You can on some 9%. All right. So with that, we've seen basic simulation here. Just want to show you that, right? And if you're having challenges, you can only use the AI assistant. If you have some AI assistant that for you to ask questions, okay? So if you're having difficulties, you can use the AI assistant to ask questions, right? Okay, and you can run and let's go to analysis. So quickly, I just want to show you that, right? What the basic simulation environment. And that's what we've done now. All right. So let's go to the third environment, analysis. Okay, so you understand what we did here, right? Any question before we move on? Okay, so let's go to analysis.
Sarah.
Yes, it's fine. Okay.
The outlet shape
Let's
we want to run keep saying
it's one, this one.
this particular use.
So what did you use? Which one of you pick? Oh, it's not connected. That's the challenge. Right. Is it connected? See what it's saying. It's not connected. So something is missing. Maybe you didn't do it very well. Check what you did well. Something is not connected. Maybe not connected. Okay, let's drag it out. Something is not connected. Can you use the start? Find out what's going on. Then we can move on. Or we do it that. Yes. Once we are done. Green mark.
Yeah, like
This one.
yes.
Oh, this one.
The green dots on it. Those green dots after yes.
No, it's just a progression showing you I mean this. So okay. So this is for the what is coming on it's a what do you call it now? It's a front-end design issue, right? It's not giving any issue, okay? It's just a design thing that can be corrected. So it's just indicating that this one is connected from here, going there, right? This is coming from here, this one is going up there. Just push it right.
How far if you are simulating?
Yes.
We supposed to have data on the ground.
Yeah, correct.
Theoretically, use the test for trying to scale them, not for even a thing. So that means we must have our mass. We cannot just enter this website and just imagine.
You can. That's good question. So you can enter and imagine, but you know it's like a how will I put it now? Okay, maybe a cook, right? That has not done any cooking, right? You want to cook a food, you've never done it. Okay, and you just start doing anything. You may what you produce may be, I mean, terrible, right? You understand? So you can go in there and do anything, but it doesn't mean what you do makes any sense. It may not make any sense at all. So you're right. For process design, like I said, you need to have the data, but there's an established way of doing it. You know, I explained that when we started. There's an established way of doing process design, right? A lot of research has gone into it. So you need to have your data. You don't need to know the balance. You don't see what you've done here. You don't know the mass of ethylene that is going to be produced, of hydrogen, right? But we need to know the inputs, right? We need to know how much of it is actually going in, right? We need to know the input essentially, the input, the component, and the processes as they will be connected. Does that make sense? So you understand the sequence of data you need, the components that are involved in that processes, understand the way they will behave, that is understanding the property package that feed them, right? You need to understand the input parameters. What was the temperature? What's the pressure, right? You know, then you need to understand the processes, how they relate to one another. Yes, very good. You need to understand that. You need to understand the reaction you're dealing with. That explains that. So if you want to do processing tests, like you might say, okay, no, I don't think this. I want to think of something else. I say, okay, what if we think of it as a CSTR? You know, that does not actually make sense here, right? Because CSTR is third-time reactor, not an equilibrium process. So there is not. It doesn't make any sense actually, right? Because you're not stirring. If it's third-time reactor, maybe you are involved in liquid. This gas, you're not stirring anything here. Do you understand? Use the liquid. Do you get the concept? So just begin to think of what makes sense, right? Without being told.
Or there's a few things going on.
So it's to the extent of connecting, it will let you know also the calculations. If you go and use CSTR, yeah, it won't tell you, it will actually give you some error, but it will convert, but it tell you what you are doing may not make sense, right? Because you have gas stream and then what are you stirring there? Do you get my point? At high temperature. You get what I'm saying? So that's what I'm saying. It's not enough to just, you can have, like I said, everybody can access tools to cook, right? Okay, but it doesn't mean your result to make any sense. Okay, so your skills, so it's a way to develop your skills as well. To do it, play with it and say, okay, this does not make sense. What can I do? So this team method cracking, you understand how it works. You can come tomorrow and try to come up with different things that make sense.
Different thing for same process of reaction.
It's a different reactor. It can okay, let me tell you something. It's an equilibrium reaction. That is a fact. So you can't change that. But that is a fundamental theory. That's fundamental chemistry. But you can manipulate it. You know how to manipulate an equilibrium reaction. Okay, you know have you heard of reactive distillation or reactive separation process? So you can, okay, let me explain. So you can imagine a case where, so understanding the equilibrium, what is happening in equilibrium reaction is that as the ethane is being broken, you are producing ethylene and hydrogen. And if you don't do it quickly, it will go back, right? But according to Clay's principle, right? If you start removing one of the products, what will happen? The reaction will continue to progress in the forward reaction, the forward part, right? So if you have a system of immediately removing maybe hydrogen within the reactor itself, then the process, then it will continue to, you can do 100% conversion. Does that make sense? So those are the kind of thinking. You have to understand the fundamentals. So that again, it's a equilibrium reaction. So there's nothing you can do about that. Right? But can you manipulate it? Yes, to achieve your goal. So it means maybe you want to design a different thing. Maybe I want to design a reactive, But of course, after you do that, you must now subject your reasoning to the physics of the process. Okay, with this work in reality. You're talking again, if you have to imagine the process. You are talking about an industrial furnace. If you've been there, you see what I'm talking about. Right? High temperature process, there are a lot of safety consideration and all of that. So you do it, and then you have to reason along the line that, okay, will this really work? That's why when you do this kind of thing, you do again detailed engineering, you do CAD, right? You do 3D modeling. That you do detailed engineering, you do mechanical design, you do PNIDs. Okay. So you do all of that to then validate, and at times you now come back. Maybe that's why engineers they work in teams, right? Maybe there's the process engineers, then they send their results to mechanical engineers, right? And then they give them feedback. And then you come and they tell you, okay, what you've done here, no, maybe we need to change something. And then you come back and redesign, and then change you get what I'm saying, right? So, but to this question of can you enter without knowing anything? Absolutely. But you need to understand what you need essentially is basic understanding. Do you understand? Okay. All right. So we've done with the solution environment. Any other question before we move on to analysis? Okay. So we go to the third environment analysis, right? So analysis environment is where you can do interesting things. You can investigate essentially. It's a place where you can investigate. Let's put that. Okay. All right. So for today we do that for that investigation. So just contain the result summary, right? this heating demand, right? How much heat is involved in what you've done, this amount of feeding, right? Or 1,000 plus. Just a sum, okay? Then the stream table, that's result table, you've seen that already. Profile, this profile is usually more for flow reactors and columns. So what is really interesting, we're going to do is case study, right? So this here is case studies where this where you investigate, study what you've done, and then manipulate the process. But this is so if you do what we've done, let's say is the basic design. You can begin to do some processing tests here. Okay, that is you can begin to investigate. What if I use a different temperature? What if I use a different pressure? Do you understand what I'm saying? Something like that. So this is where you can do it without changing your primary simulation. You get it? You can change, you can manipulate variables without changing your flow sheet. The flow sheet is so here you want to analyze, So let's analyze by block. All right. Let's analyze the reactor condition in the reactor. Okay. This reactor, I want to manipulate the temperature. All right. So it's giving us the range 680. It makes sense. In fact, it's telling us already automatically the typical range, right? This 680 is the what do you call it now? The limit for before it enters reactor zone. You understand? Okay. And 120,000 is like the I mean, it shouldn't be more than that, right? Okay. So yeah. So this is what assume from 680 to 1,020 in 5 points. And it's divided into 5 points. 680, 7 something. You understand? Up to 1,000. And what do you want? What makes sense to wash? What do you think would be a nice parameter to evaluate? Can anybody tell me? Conversion of what? Very good. Conversion of ethane. And how does the conversion of ethane react or behave? You know, with the temperature. Does that make sense? How does it vary with temperature? So, which stream is that? S5, right? Ethane belongs to S5. And molar flow was no, it's based, it can be total flow. We're not looking at total, we need component flow, right? So let's see. So per component, right? You can do move flow, mass flow, anyone. I mean, just conversion of overload flow, it doesn't matter. Let's just see mass flow, right? So of ethane. Okay? So let's run it and see what happens. See what we have. It gives you a nice plot. See what we have. So it's telling you that at 680, the amount of ethane in the product stream is 674, 94, 679. That means that almost 700 of it is not, almost 70% is not converted. Only about 30% is converted. Does that make sense? Right? At 850, our process condition, right? 210, this is what we call, right? It means 79%. So this is a poor result, very poor. Of course, you don't want that. At this, almost everything is converted when you actually push forward. One thing interesting about this kind of thing is you begin to see this does not make sense, right? This is too much trouble for too little gain. You know, to increase even by from 850 to 870 is not a small thing, right? These are difficult things, right? So these are too much trouble for you to be saying. So that's why you usually stop around 10. And you even produce unwanted reactions even faster than before. Do you get logic? That's why these are what says this mean. So I will say, okay, you are deciding what to do as an engineer, right? So if you are given this kind of data and you look at it and say, what should I do? If someone tell you what temperature should I choose there for my process, right? You go to this and say, no, it doesn't make sense because see, it's an exponential behavior. You can see it in the plot, right? It's decaying.
Putting too much to gain it.
Yeah, you are using too much energy to gain too little. So why don't you just use a recycler? Just recycle it in some way. Because in any case, even I was going to separate it anyway. Do you understand what I'm saying? Look at it. Either 850, 90 by 1,000, I will still need to do a separation of ethane. So what's the essence of now increasing the temperature to? Doesn't make any sense. Do you get logic now? So I'll rather stop here and then go and separate this one. So by the time you do this analysis and then into the economics, so if you go and design this process, economics, you now realize that you'll be spending maybe 2 times of what you need to spend here. pressure. Let's see how to do that. Add the second break and see what happens with pressure, operating pressure. All right, the same one. Let's just even four. All right. Okay. The same thing. So let's run it. Let's wow. See what we have. See this one's going on. It has. So it's giving us. Pay attention. It's plotting the temperature for us for different pressure. This is at pressure of this S5 of 4 bar. So it's going in the order of decreasing pressure. So what it's telling me is that you need temperature to be lower to increase conversion. Right? Look at it. The lower the pressure, which one is lowest pressure? Here now. The blue line. At 1000, what do we have? Or less than 850. The blue line has the lowest amount of a thing coming out. That's the highest conversion. Right? But then it increases as pressure increases. Right? It means the amount of ethane coming out that are not converted increases as pressure increases. So you want to minimize pressure. That's why this is also an influencing factor for the way this process is designed. Do you know the actual gas, pressure of gas as it is hitting as it is actually coming out? Do you know who can guess? It's over 20 bar. Do you know that? The gas itself, if you were to work with it, or steam, even steam. No, the steam is at what, 2 bar, right? But that steam, typically steam of that steam, the high pressure steam, it should be about 30 bar, right? But there's no way we can work with that. Or that will jeopardize the system. It will be a mess. So that's why it has to be depressurized. The steam has to be, you have to lower the pressure of the steam. That's why we're working with 2 bar. Does that make sense? Yeah. Right? That's why we have to. So if you are wondering why 2 bar, maybe someone, why not 10 bar? Maybe you are wondering, you want to play with it. You can come and do this and say, okay, and see what's happening. Okay, you realize that you can, so if you start working with 10 bar, you'll be getting a very poor result. Does that make sense? So the analysis, in fact, with this kind of analysis, you can generate hypotheses. For someone doing research, are you following? For someone doing research, you can generate hypotheses, generate theories, and then go and test it. And then work with what in my show, what I found is you then work with people in doing experiments. And then, can you help me? In fact, at times they come to you, they want to check something as well, And then you work with them together. Because you are discovering some result, interesting result in your analysis, and then you can work with people doing experiment, and then you work collaboratively together. In fact, I believe that process simulation is actually a low angle fruit opportunity for a low resource environment like Nigeria to do great research. Do you know that there are some papers published, some research work done based on just process simulation and things like this, the computational work. It's not in like a place like Nigeria, we say, okay, we don't have much resources, right? Lab resources in our academic institution, right? To do ground research. But we have an opportunity with tools like this for a low hanging fruit, right? There's a low hanging fruit for us with fruit like this, tools like this to actually do good work. I can tell you for a fact, if you play now with this kind of simulation, you begin to develop real hypotheses that can be validated with literature references. You can generate something and then you're able to validate that result with what has been done before. Maybe you are lucky, you find an experimental work done by someone somewhere and validate your results. Does that make sense? So we have a low angle fruit here, an opportunity to actually, in the absence of the cost, right, the infrastructure to do detailed maybe experimental research, we can work with things like Query Simulator to do good work. Does that make sense? You generate hypotheses, test the theories, and different things. All right. And I tell you, we are even still further developing this aspect of so you can do more complex analysis. Right? We want you to be able to even do conversion, right? We are not measuring conversion here, directly. You are measuring a thing that is living. So then you can interpret yourself in your head, right? But it would be nice for you to calculate conversion directly from here and then see it so that the analysis is straightforward. Okay. All right. So that is that. Then there is energy. So essentially what you do with energy is pinch analysis, right? Calculating the minimum possible energy your system can use. There's not much of pinch opportunity here. So not much is being done yet because it's a simple process. If you begin to do more complex simulation, you begin to see opportunities for heat integration. And that heat integration is another massive opportunity for synthesis for that. So you are asking about processing the opportunity to, can you do it yourself? In fact, the best way to place to start as a chemical engineer, as a process engineer, to begin to do process synthesis, common like this, heat integration. What does that mean? Trying to find opportunity where you can minimize energy loss. There's a lot of energy loss opportunity here, right? You produce you have 850 degrees Celsius, very hot gas. Yes, rapid quenching. In fact, there are many innovations around that. If you design a plant here, the way our heat system is designed might be different from. So that one is a easy place for you to start with innovating. Do you understand what I'm saying? Because you cover your heat in different ways. The fundamental process, they're the same, but the heat, how you recover your heat might be different. Does that make sense? Okay. And maybe your own method saves us more 10% in CapEx compared to or in operating costs. And that is where even for an employee, okay, that is just working in a plant and does not even know the opportunity available. With simulation, you can understand your process and begin to see opportunities available within your plant to save money. Okay. Then there is economics, right? So with economics, you can do this. Is a very important feature, right? You can calculate the capital cost for your plant, right? Calculate, so you can size your plant, right? The heater, we have two units there, heater and the reactor. You have the size of the reactor, right? And the size of the reactor. Okay, now this you can go back. I will advise. Don't rely on this. Do a check. You have design equations, right? Use your design equations to corroborate this parameter, and then you can choose the materials of construction, right? Different materials based on what makes sense. That's this. For example, the reactor, you can't use just carbon steel. There's some high alloy material you need for that reactor. And again, I expect you, the ratio of the reactor is even different than conventional gas PO, right? It's not like if you want to do a model simulation. Let me go back there. I want to ask a question. Now, we did something now. I want to ask, as a simulator, we use Gibbs reactor to do the simulation. If you are to do a more rigorous simulation, what unit would you use? Let me show you what we have here. We have conversion yield equilibrium Gibbs CSTR PFR. Who can tell me what would be a more accurate model to actually use? Who can explain? Who can tell me? Equilibrium is the same as Gibbs, right? I just told you that. They are the same. Given your understanding of how that process works, I just told you how it works now. What would be the most rigorous way to do the simulation? Anybody?
Sorry.
No?
Reactor.
No, we use Gibbs reactor.
You can't use CS because not Gibbs.
It can be system.
You cannot carry.
Yeah, that's a PFR, right? Fluid flow reactor. You know what a fluid flow reactor is, the way it works, and the way it is sized. I explained to you how that reactor works, right? You have the pipe, just flowing. The continuous process. Reaction takes place as the gas flows through the pipes, right, within the furnace. So that's a fluid flow system. So if you use that, it is more rigorous. You need to specify a lot of things. You need more data. Does that make sense? So you need reaction, you need the reaction equation, you need the profile of the temperature, you need all of that. Do you get what I'm saying now? So you can do more rigorous work. In fact, if you are going to do this for maybe proper design, industrial design, you can't use the equilibrium system. You have to use the fluid flow. But that means more work. Does that make sense? That means because you have to specify the details, the temperature profile, the reaction, even the kinetics, right? You have to specify the kinetics of the reaction. Do you understand? Okay, I just want to put it for now. All right, so the economics, right? Choose the reactor, the materials of construction and what else, and then OPEX, right? That's operating costs for that plant. Can do profitability analysis. Does all that calculation for you seamlessly. And you can change assumptions. Okay, maybe this is based on cost of electricity in South Africa or something. You change it to what is really for you, right? And change the all these parameters, cost of cooling water, change all of that, and then it updates. Then you can generate a TE report, economic analysis report. All right. Let's try to generate that based on what that's done. So yeah, so it's a TE report. It tells you operating hours of 8,000 hours, right? The nice flow sheet for you, and tell you the equipment size, cost and sizing. Right? You have to confirm all this stuff, right? Putting cost and revenue, tells you that, gives you all the nice economics for that plant. Okay. I need to go back. Okay, so do you understand? So you do all of that. Right. Now let me show you that. Now the good thing what we have here, so especially for students, we have a connect platform. Look at this. First, let's save it. Let's name it. Let's name it as thank you. So name it as thing and you can save here. Okay, you can save here, but you don't want to lose your job. So save, look at it, and you don't need to save it. I mean, any folder on your local you can save there. You come back once you log in, you save it. And you can do something very interesting. You can share it. Now this I want you to look at this. You can publish to what we know as LensaSim Connect. LensaSim Connect is an interesting platform where you can showcase your work to others and to employers. Yes, I'll show you how it works now. So let's publish this to LensaSim Connect. Click on it. That's it. So let's open the post page. You see this? So can you see? This is what I did. This is my name, right? It's showing my work now on LensaSim Connect. Okay. And if someone were to come here and look at this, they can fork and run it. What that means that they can open a copy of this and try to see what I've done. So you can send this profile. Let me go to LensaSim Connect proper. So that I will show you how the confidence this one step. Okay, this is it. This is LensaSim Connect on LensaSim.com. So it's loading. I mean, these are the different work people have done. Right? Oh, did someone just posted this? Someone from here just did this, right? Where you doing? Who was busy? Yeah. Oh, nice. Nice. So your work is now already appearing here, right? You didn't know, right? Nice. So that is your work. What you just did. So you can always come here. I mean, create profile so you can edit and create a profile for a profile. You understand? Do you understand? So this is what I posted just now, right? So this is what others have posted, right? So essentially, and people can interact, can make comments, and ask you questions from here, right? What's your name again? Name comments. So I can ask the question, explain what you've done. I can, explain. I mean, whatever. Yeah. Right? So that's a comment, right? You can come and respond and you understand what I'm saying. So what this does for you is that, just like GitHub. I don't know if anybody knows about coding, all these coding people. So with GitHub, what GitHub helps all these developer does is they can they showcase the work they've done, and then they can now share that profile with employers who they want to employ them. You understand? And then they can see, do you get better? So in the same way, you can come here Let me click on my profile. Right? So this is my profile, right? So you can copy this link and share it. You can put it on your CV, send it to your employers, or you can share with LinkedIn or X. You see, so someone comes here now, they see what I've done. They see my simulation of 5, and they can ask me questions. They can open it, like I said, you play with it, see the reasoning behind what I've done. Do you understand? So that is a valid way of demonstrating your skills and expertise in process design and process synthesis to employers. Do you understand? So this is why I want to show us LensaSim Connect. Okay, so it's very powerful. Other things I want to show us. Let me see if I can go back to LensaSim. So this LensaSim Connect. Let's go back to LensaSim.com. So if you go to LensaSim.com platform, for faculties, classes, there's a classes picture, right? We talk about how valuable a lesson to prayer simulation is. So a lecturer, maybe you are teaching the design course, let's say NSChE 4 or 5 or whatever. So design. Only design, right? Then just add that course. Okay. Okay. So that course has been created, as you see here. All right. Let's click on it. So, as an instructor, it is a platform for you to create assignments. You can create assignment for your students. Okay. So they come here, you create new assignments, right? They create some and all of that. So I want to, and you can even generate assignment with AI, right? So you can either prepare it yourself or you generate with AI. So let's try with the AI and so I just click on this. All right. So with that, just to send a prompt. Okay, let's say create an assignment. Theme. So generate the switch over So just need to specify that thing like level, because we are trying to design LensaSim for not just for investing, but we want secondary school students to have to begin to appreciate it, So you can make for any level. So let's say investor or corporate, right? And you can find the standard, maybe standard or cutting level, and how many parts, right? So let's generate the assignment. So it's going to take a minute or so, and let's see what it creates. So it's generated right now. And as you see other things, it generates a code. This is a lesson code, the code for the class. So you can copy this code and send to your student. So the student use this code, come to the classes, just put in this code, and then you take the assignments. Does that make sense? You can join the class to see the instructor's assignments, things that needs to be done. And then you can interact. So lecturers and students get to interact on LensaSim. Do you understand? They're using the classes feature. Okay.
Can you stop with the very first? Generate ways to save energy.
I wouldn't want you to do that. Because why you can do that, but it's not a good thing to do.
Why?
Yeah, because you are outsourcing your ability to reason, right? In that case, AI is very good, but especially for students, I think there are certain things you try to avoid using it for. Especially if you're going to develop, you can do it if you want to learn. Maybe ask about party package. I don't expect you to know what that means, right? It involves some work based on some people's PhD that leads to all that, right? So you can ask, okay, explain why should I choose PSRK? Those kind of questions. Yeah, why should I choose pengobicin over NRTL? Those are the kind of questions I would expect you to be asking. Not helping you to synthesize. Does that make sense? Right? To synthesize, you need to think through. I mean, you may get stuck and maybe you don't know why is this not working. Yeah, you can go and ask. Just like think of it as you have an instructor or a teacher that you can ask for questions to guide, but not to actually do the work.
Yeah, thank God.
Yeah. Do you understand what I'm saying? So it's generated now, right? Okay. Generated submit. As we see, so if you generate the title, right? The eight instructions, okay, and you can edit it. It just generate general instructions, right? What is plain, right? The things that you'll be looking for as a lecturer. The minimum function, right? In the Ventolin, right? Just change all that. You can edit, change it, okay, to what you, or it gives you a template to work with to start with. Okay, so you get all of that for you. These are the things you want to see. Oh, quacking is stronger and determine, okay, the highest should be, all those things you specify. I think conversion is looking at -5. What? Okay, 0.65, right? So as a teacher, you use this to, to generate, and then you can create and publish, or you can save as drafts. After you've done your editing, you edit it, change it. All right, so it's you see the assignment has been created. So if you click on it, if I were a student, and I click on this assignment, okay, I can start it in simulator. Just open the starter, right? You see what you need to do. It will take us to the simulator, and you can see it's telling you the assignment. And when you are done, you can submit for grading. Do you understand? So you are doing your work here. It gives a template, of course, based on what this assignment based on what is generated, right? So it's like one test your understanding, certain things. It has used something already. You get it. So then you do all of that and then you submit. Okay. So let's see what the other tests we can do. So under your profile, you are there learning courses. It is very useful. So learn, okay, this is my dashboard. So learn there, depending on your level, right? The corporate person can learn different things. On a university student, let's include only parts. So you can come and learn different aspects. You can learn recycle structure and convergence, right? You can learn how to choose the part method, right? We talk about part method a lot today. So you can learn about that. You can learn shortcut distillation design. Now, when you start doing those kind of simulations, those are more complex. What we did is simple. Let me tell you. Okay, what we did just now. We used a simple heater and equilibrium reactor. Equilibrium reactor are one of the simplest for reaction. When you start doing even CSTR, all those are more because you need to specify more things. You need more data and they have to correct. Do you understand? So this can guide you. Fair distillation can be tough also to split, right? Senior design, azeotrophs, NRTL, different lessons. Okay. Do you understand? So a lot of things can be done, right? Then there's certifications. Okay. So you can, if maybe an employee, you can come and get a certificate on Waste Simulation Association that enhances your employability and that gets to even be more, to a better position, right? To get someone a promotion, right? Because you will enhance your ability to save your company 10% of operating costs per annum. Do you understand? So these are paid. Say if you are working in a plant or even maybe working as a process design engineer, something like that. So okay. So so different aspects could any certification involving minerals and metallurgy, gas processing, and things like that. Cost engineering. Okay. So what else? Yeah. We don't have employers here. I don't assume we don't. I will have gone through talent search, right? So the connect, LensaSim connect. Then you can go to LensaSim connect from here. Before I go there, see there. So the that LensaSim connect. I mean, it's a world of opportunities, because ultimately employers can search your profile, and search your profile and see what you've done, and maybe that then land you jobs. Do you understand? So I encourage especially students to get used to LensaSim Connect. All right. Of course, you can't use LensaSim Connect without using the simulation platform, because you will need to do a simulation before you can post anything. Do you understand? So yeah, go ahead.
So this website, LensaSim, is it already is it widely known in Africa?
It's not widely known. Okay. So let me tell you how it works. It doesn't have to be widely known. Okay, because it's individual. You create some simulation, just like I showed you, my profile. All I have to do is just to click the link and go and put it on your CV. It doesn't have to be known to anybody, right? Or put it on your LinkedIn profile or whatever. So the employer look at it and go there and see what you've done. It's like a profile of yourself. Does that make sense? It's a profile of what you've done with respect to process simulation, right? And then you can share it. If someone is even evaluating your ability to, you just send them without even sending your CV, you can just send them that link. Go and check what I've built. Do you understand what I'm saying? Right? So yeah, I think that's mostly it. If any other question? Any other question? Yes.
This simulation, does it like detect mistakes? Let us know I'm doing something like that.
Does it like what?
Does it like
Detect?
Yeah, mistakes.
So generally for every simulation, right? If you just say, for example, when you are doing something, right? When it doesn't converge, when you have not done something correctly with respect to that simulation, it tells you.
Okay.
But that's the limit. It tells you where you are wrong with respect to the fundamentals or the thermodynamics, right? The guiding principles, I mean, to tell you clearly see the error, to tell you that. But beyond that, they can, for example, when you're doing the flow sheet and you're not able to connect something, it tells you that something is not connected, right? So those you will tell you, it will tell you all that.
That's the thing.
That's what it will tell you. That's a simulation. You understand? It will tell you those errors. So if you always specify certain conditions that doesn't make sense, it will tell you, explain to you, and you see the explanation. Every thermodynamically this does not make sense. This makes no sense, right? In fact, it will calculate. You can even check your result and see that the result is not making any sense. Do you understand? It may just maybe converge, or at times it will not even converge, right? So those are there, but it can't certainly tell you things like how to come up with ideas, parameters to use, all those things. You can ask, and if you're asking for POES design, this is one of the important uses of the AI for POES design. If you don't know the parameters to use, right, you can always ask, okay, what should be the input?
I see your mother.
Yeah, I think so. Let me read.
Sure.
That's
Yes. Any question?
How often are level besides the coins compared to those stuff?
Compared to industrial, very good question. So that's a fantastic question. Yes. Yes. I mean, I love that question, and I'll be honest with you. So let me tell you something. Aspen Plus, Aspen Plus, right? They have one of the major key elements of a simulator are the data it contains, the data it has, the component data bank. So Aspen has over, if I'm not mistaken, over 30,000 species in their database. That is, if you're looking for any component, think of any chemical, you can find it. We have over 3,400. Do you understand? This is the limit. And I'll tell you why. Some of those data are proprietary. You can't just access them. They are protected by patents and things like that. Some of them are based on laboratory work. Some people have done, they came up with new species, maybe doing some chemistry work led to some different kind of chemicals. Aspen sort of has those kind of things, and it's backed by some powerful forces, So it has those, you get, and other simulation software like that. What we have are what are publicly available that are not protected by any IP. Do you understand what I'm saying? So to that extent, it's limited. So it means that if you want to do some simulation and the species is not available, we don't have maybe some complex species that then you can't use LensaSim. Does that make sense? But of course, that's why if you go to our website, one of the things we say is this is wanted to be primarily used for learning, because there is no limit to you using it for learning purposes, right? Of course, when you start doing some certain complex industrial work, you might not be able to use it because of those limitations I explained to you. Does that make sense? Yes. Right? So, but for learning, of course, academic purpose, there is no limitation because you have enough to work with. Does that make sense? Any other question?
Mine was for the second use.
Okay.
Rather to appreciate you.
Thank you.
I have a job for investor business.
Oh, a pleasure.
So I've done this background of the studies.
Okay.
On behalf of the I'll be seeing my practice.
Okay.
Yeah, we are bringing you back. Maybe not for the section as a particular for we discuss.
We'll be so good.
Okay.
See how just this tribe.
Okay.
With that testing.
I can feel
Atmosphere where maybe comparing between your app and that of either risk.
Yeah, PwC, yes.
Should part be able to say things about security what's in terms of teaching, and I think yours is there just students that also should for the lecturer
Yes.
sign there like there so I'm English projection take a big system. Absolutely the level of development with this so far.
Thank you so much. Thank you so much. I look forward to it. We'll certainly want University of Lagos to take a lead in deploying this for students. Okay, great. So
This is
no last, no convenience.
yes.
And they know each other.
Well,
So, see you later.
see, yeah, everyone, that's about
so
it's really so.
that's perfect.
Yeah. Virtual something.
But your school, because your school can, so you don't, because right now there is indeed. Let me even talk about the subscription packages actually. So there is the free version for students. You can play with boys. Indeed, there are limitations to that. You can only work with 10 units. So you can't do much, and there's certain things you can't even use, like the economics. Some of the analysis you can't do that. That is a free version. That is just maybe some simulation. Then there is the pro version, right? $5 per. That is how much naira? That is about 7,000 naira per month. With that, you can do more simulation. You can do more flow sheets. You have access to everything essentially.
If the site
If the school, let me get it. If the school pays for subscribe, then you have the lecturer student package. The student are not paying, so the school will cover it at that. You understand the logic? So the school will take care of it, and then it will give access to both the lecturers and students and the different packages. So ideally, if you're a student, you shouldn't actually be paying for it. The pro version is ideally suited for employees, people in industry, right? That want to you get logic. The what for a student that is active, in the university, ideally should be advocating that your school subscribe to LensaSim so that you understand what I'm saying? Because it becomes a teaching tool that your lecturers get to use and things like that. Any other question? Okay.
Question here. Is from engineer Ogun. So I don't know, why can't you speak? Is it not better you speak? So, okay, let me bring out his question. His question is how much. Sorry, the first one is what is different, or what is different? What is its differentiation from the Cape Open,
Okay.
Chem card, and IC software?
Thank you.
Okay, so that. Oh.
Oh, there are questions there actually. Okay. So let's be answering this question actually. So very good question. So one of the imperfections, one of the when I talked about the motivation for doing this, I talk about look at the title, modern process simulation. Actually, for us, what modern means accessibility. If you look at the difference between the tech era, maybe in the year 2000 compared to now, what's different? More access, right? Greater accessibility. So the fact that we are democratizing access, now all those software we talk about, they are not, for us, you need to install them. They are heavy, right? Hard-coded solutions, sort of. But with this, you don't, in fact, you can access it from a mobile phone, though you won't have the best of experience, right? But want to democratize access, at least it becomes something that you use every day easily. You're not restricted from using it. Does that make sense? That is the major difference. Second thing is cost. In fact, of course, there are some of these software are also free, like DWC, right? But they don't offer as much solutions as we have. This is an integrated solution, not just for simulation, right? If you look at the way the legacy software approach simulation is, they think of it as more of an industrial solution. Does that make sense? Just something for the industry. And that's how I pushed as well when I was first introduced to it in my final year at Unilag, is to think of it as a thing I need to learn so that I can be able to get job. Does that make sense? But it's beyond that. You get logic? So that's the way they position it. It's more for industrial solutions. It's what you find us. That's not really been designed to enable learning, in particular in Nigeria, right? You understand what I'm saying? In the US, for example, they have license, right? Subsidized for students. It's still expensive relatively, right? But they have something like that, and students, like I told you, they actually go through it. Okay, so this is designed to actually be a platform solution. You could see the connect solution there, right? That is a platform solution to actually develop skills by students, employees, and lecturers and researchers. Like I said, the process sentences, you can do more research and the access is there easily. So it's a major difference because we are democratizing access, not so think of it as a solution that is within reach easily, and it's not something that you'll be thinking of. Do I even have a system that I can install this thing because of the requirements? Those kind of things, right? All you need is just a web browser and you're good to go. Okay. Can we go look at the next question?
And it's giving another time. Yeah, time.
How much does LensaSim cost? Nice. I think I've answered it. So Like I said, we have the pro version that costs $5 per month, right? And that's just about 7,000 naira. Okay, that's available for anybody that just want to have access to it. And then we have the student, the corporate version, enterprise version. For that, it's customized. It's based on the discussion, right? Because we have different package. It depends on the size of your need, right? Maybe you have 100 students. Someone that a school that has 100 students has the cost is different from someone that has 500 students. You understand? So and then we can always discuss, but it starts from $450, right? In that case, per annum actually. Is it per annum? I think it's per annum. For school for corporates, and that is about 700,000 naira per annum. Okay, so that's the starting. That's where it starts. So, but then when it's custom, so we can only discuss. But standard for, $5 per month, anybody can access all the features. Again, there's free version, but again, it's limited. You won't really enjoy it. Unlike we subscribe and we are not limited. You understand what I'm saying? Yeah. I'll pass that pricing question. Let's speak on Yes. Okay. Who answered that? So you put the link to the on it. Okay. So I think so.
Because I'm more.
Okay. Yeah, that's right. Okay. Yeah.
I really try this now.
I'm pressing with you.
No, it's not with us.
It's important to learn that.
And that person is not with us. The best of is one that share the link with connect that one with us.
So that will you answer my question.
Yes, that is question.
Yeah, that it's important to understand.
Is it a question?
No. Like that's if you answer the question.
I think it's not with question, not with us.
Yeah. Like opinion. Like as opinion.
Yeah.
It's important to know the basics and fundamentals. It says enjoy food and colleagues.
To enjoy the absolutely, that's correct, right? I told you, right? You need to, that is the essence of your basic, your classic theories you've learned, right? Those things are important because now you are now demonstrating what you've learned. Yeah. Who is that? Who's asking about contacts?
Can you speak?
Thank you so much, sir, for a lovely presentation. It's wonderful. You've answered my questions. I wanted to get something about differentiation. You've already answered it, the democratizing part. And I understand there's even a community that enables learners to, be able to collaborate, maybe work together online, stuff like that. That's fantastic. My guess is there's probably some AI blended inside that also ups the game. Thank you so much.
Thank you. Okay. All right. Yeah. Let me give this person thumbs up. You could see what he said, right? That is why we built it, right? And we paid for, even when then, we paid for training and we could not even access it. With LensaSim, you have access to everything. All the trainings you need and the platform itself. Platform, the training, and more. You can share your. So it's an entire ecosystem that solves the problem for you entirely. Does that make sense? Yes. Any other question? Okay, I think if there's no other question. I think with this we come to the end of the workshop. Thank you very much.
This is to appreciate our lecturer, Dr. Peter. We thank you for all the insights for today's program. On behalf of NSChE Lagos Ogun chapter, we do appreciate you for taking out time to have these long interactive sessions. We can see that everyone is happy here. You can see they are farming to eat, so they really enjoyed it. It's very, very straightforward. LensaSim, very, very straightforward. Once again, Dr. Peter Oladipupo, we thank you so much, and we hope that you will still come around again to really take us through an extensive workshop more than this to showcase this. I'm really impressed. We pray that God will continue to bless you. So let us have a photograph. And let me connect it so that I can take the screenshot. That. Just for screenshots. No, just that. The screenshot will just show. This one will not show really everybody connected. No, I've taken all that, the topics, but the number of people that joined.
Yes, you can use it.
I wanted to take it, but I just saw that you removed it. Okay, we good.
Also, no, you don't need. You understand for our records. All the children to bring all their needs to them. On you, have that. Oh, yeah. You understand? Well, where everybody quite a
Use this one. You know, but
they don't really need to talk and
it brings, but not the numbers.
they don't bring all. It's like it means.
Okay.
I don't know. That's how I should